Alright, hey guys, and welcome back to another sort of episode of working with the ALU of the CPU. And actually, we're not going to be doing the ALU today, we're going to be doing some of the RAM, or rather the registers. So, to go ahead and look at this, what I've done is I've made a small area of the instruction set architecture to have all these ALU bits of P0, 1, 2, and 3 defined as not A or in logical mode and or select, not B for P1, carry in addition mode for P2, and in logic mode differentiation between XOR and move. Then the further thing here is going to be the pin 3 will determine arithmetic logic. So which mode the ALU is in. Out of all these different possible instructions, I've made a subset here based on the pinouts. Obviously, each opcode could have its own value, but for example, add, subtract, increment, move, and the bit mask clear, OR, and XOR. And that's basically all the common valid instructions that I've created for the ALU. So looking back to Logisim, I've made a very brief design of a D flip-flop, and this D flip-flop is on the falling edge of the circuit, meaning that when the power turns off, it sets the bit. So if I turn the data wire D on and off, it doesn't actually affect the input unless you have the right line enabled, which would be enabled on a clock speed, on a clock itself. Which then will say, okay, let's say data wire now. Notice that it's not turning the bit immediately because that could cause issues. For example, if you're reading from a CPU register and then CPU register outputs something over here, and then you immediately set it, then it goes around the loop again. That will become a big issue on data values. So once the right bit turns off, it's saved. And then the data bit can be turned off. And then that way we kind of ensure that our data bit will be properly saved into Q, which is our output. And then Q as our output, we should actually add something here, which would be the read line, which would be asking for set data. The reason that we have to have that delay there is that, for example, if I have an operation here to add A plus B, and then I'm reading from register A out to the ALU, and then I'm going to go ahead and say, okay, now that we've taken from register A, we're going to have to do the next thing, which is, some other operation on A. We can't have it be done on the all done on the rising edge because it creates a feedback loop that could be undefined depending on how long that clock goes on for, and will give you the incorrect results. Furthermore, we couldn't just have it all be set at once and all that. So this is the best solution, which is a master slave. This is the D flip-flop implemented in NAND logic, and over here is an SR latch in NAND logic, which then goes to Q. And what I'm actually going to go ahead and add into this input is going to be another pin in, this time facing south, with a label on the north side. That's going to be the read enabled. So it's going to be R. So in order to make sure that we can get an output here, we'll have to have an AND between the read bit and I don't want to get rid of this wire. Cool. So we're going to have a quick little AND between the read bit and the output bit. So if we're not reading, we're not even going to get the result. That way we have a compact sort of memory cell. So only once read is enabled can you get the output. Similarly, you can't change the input unless write is enabled, for example. And that way we can have a nice and easy way to control reading and writing from this D flip-flop. So I'm going to go ahead and make it into a nice little module here, where we're going to go ahead and have an output on the right side. I like the idea of left to right sort of logic with circuits. Of course, you can have your own preferences. I don't really care. Let's set this to be a right size, right? Have to be one bigger, maybe. It's really hard because I don't have too much control because this window is so small. I swear I just changed it in size. Okay. All right. So we have our output on the right side here. On the top side, we're going to have, I believe this should be the input for the read line. The data line is on the left, the top left, and then the right enable line is on the bottom left. And then we can get rid of this little curve here. I don't know why those exist, to be honest. Is it just to tell what orientation it's in? Potentially. Then we'll just have a label on, although having a label on it just tells you anyways. So this is some SRAM. So this is SRAM 1 byte. So the reason it's SRAM is because DRAM uses capacitors, and I don't believe we have anything to do a proper capacitor here, so it has to be SRAM, which is gated logic. It's better to use DRAM because it's more compact in real life scenarios, but in this case we don't even have the option to really choose, so we're going to be using SRAM. So this is our nice little circuit here. It describes pretty much a data read, write, little unit here, and this is one single bit. So what we can then do with this SRAM is that we can chain it together into a 16-bit full thing, and then we can use some demultiplexers or decoders, whichever you prefer, to go ahead and read a specific bit from a specific portion of the memory cell. So let's go ahead and create a new circuit here for the SRAM. This is SRAM for 16 bits. And then, well, it's gonna be like a 16 by 16 yeah, I'm trying to explain it, but it's gonna be a matrix that contains a bunch of SRAM. So it's gonna be like it's gonna have 4 rows and then 4 columns. So it's gonna use 2 bits to do that, to specify, and then we'll do the full 4 bits to get more, and then it will end up being 256 total, and 256 bits total. Either way, SRAM 16 bits, and let's go. So we're gonna take our SRAM modules, right? That was a 32-bit not. How did I click that one? SRAM 1-bit module. And then we're pretty much going to try to do them sort of as a matrix. So we're going to go ahead and evenly space these apart, right? And then we're going to go ahead and say that the read enable line is going to be, it's going to need its own input, right? So we're going to have read enable. So this one's going to be the, well, pull behavior. Hopefully it didn't change anything there. I didn't see if I did. So we're going to have the read enable line here. If we take the read enable line, then we're going to pretty much look at what we're going to be reading from. We're going to have to take in the 2 bits for the address on the top and 2 bits for the address on the bottom side. And that way we can have addressable RAM. So I'm going to go ahead and make it spread out here. And in the future, I can actually just spread this out, probably more. This is probably a little bit too compact of a design, but We'll take the SRAM here. And then we're going to take the 2 bits of, so we're going to have the read enable. We're going to have the write enable, right? And then we would have a data bit as well. Of course, if we're not doing writes, data bit is ignored, right? So the way that we have to go ahead and take this is that we're going to go ahead and say, all right, we're going to take the data line and plug it into the data area of every single unit. And that's pretty much just going to be a little repetitive system that goes ahead and says, oh, we're going to write enable each one. Or sorry, we're going to have the data access to each one, right? Of course, if you're not writing, it doesn't do anything. It's also technically an invalid state, I suppose, to have oh wait, no, it's not invalid, sorry. If it was a normal latch where you're trying to read it while you're trying to change it, that causes a lot of issues because it's not synchronous. So for example, if I was trying to read from the cell for an SR latch, it would go ahead and read out the data, and then it would pretty much be reading out said data, and then it would also be able to be changed at the same time. So you could read something that changed at the same time, and it could cause some pretty bad issues. So that's why this sort of locked down design on the falling edge makes it a lot more secure, because you know that for a fact that it's defined to be on the falling edge. So what I can do is probably space it out a little bit, which is really nice because we just have this nice little unit here. Why did simulation mode go off? Okay. Either way, now we can also take the read. So the read and write line will actually be based upon where the intersections are. So now we have to have a matrix, basically. We have this entire thing divided into 4 rows, 4 columns. And we can go ahead and take in an address sort of pin. So this would be adder. So for our address, it's going to be 2 bits. Well, actually, total is going to be 4 bits to find a memory address in a 16 cluster, because you need 4 bits to represent 16 values. And then we're going to split it and then use the high bits as one part and the low bits as another part. It doesn't necessarily matter actually where it is, because you don't really care about the physical location of the memory. You just want to know the data at that address. So we can go ahead and do a splitter here with a bit within a 4, splitting it out 2. And then we're going to go ahead and make it right-handed so it's facing upwards. So we take the address, now we've split it out. Now that we've split it out, we can then go ahead and use each input, right? Or each set of data. Let's throw this a little bit over there. And then we can use a plexer, right? We can use I believe we can use a demultiplexer, correct? Select bits is going to be 2. It doesn't need an enable. Then data bits going to be 1, right? So if we take the demultiplexer, it's going to take in the signal bits, right? Or what's the top side? Select location is the bottom left. Oh, okay. That's fine, I suppose. Oh, sorry. I actually do need a decoder. I think. Methinks I need a decoder. Yes. Select bits of 2. Then include enable now. Yeah, this is what I wanted. Okay, my bad. There we go. We have a decoder that takes in the select bits and then says O for whichever address is going to be enabled, right? So if you see here, we have these 4 lines are enabled based upon their outputs. So that's pretty cool. So then we're going to go ahead and take a decoder once again. Now we're just going to go ahead and input this to the top right, and then put it here. And now we have our own little matrix that says, oh, which bit are we selecting? So then we're going to go ahead and take whichever the output is. So we're going to have to go ahead and take whichever output, and then we're also going to have to AND it with read and AND it with write to figure out where we're doing that, right? Or where are we going to be reading or writing to? We know that, and then we can go ahead and do that. We also need to know the exact selection location. So I suppose we should treat that in such a way where we take identical lines out. I'm wondering, can I make this larger or no? No, I can't. Okay. So I'm going to split it apart, kind of. 1 over, 1 over, 1 over, then 1 over. It should actually be like 2 over, shouldn't it, though? So just to have an even spacing, I'm going to make it 2 over, right? Cool. And then we would take each one, and then we have to figure out with the other decoder. So let's go ahead and take that, gonna do the same thing here, and then go ahead and do the same thing over here. So now we have decoder, takes out these outputs, kind of looks like a jellyfish, if you think about it. I don't know why I'm making that comparison. Hello? Decoder. What's the issue? Length is 20. Data bit, what? Right. There we go. That was strange. I'm not gonna lie, that was pretty strange. Okay. Now that we have this decoder unit, both decoder units, then we're going to have to do the pretty much the union of each, checking each, right? And then we know where the location is. So this ends up becoming some logic where we're going to take some gates, do that. I want to make these gates small, as small as possible. And then I want it to face south. So if this one is selected right, then we can go ahead and say, oh, we're going to go and put pass through read and write, pass through read and pass through write into register the first part, right? So then we're going to go ahead and pretty much do the same exact thing for each one, right? So in order to do this, I think we're going to need to reformat this a little bit more in order to make room for this logic. Not 100% sure. Let's go ahead and take the AND gate, make it narrow, and then we're going to have a read pin, right? Let's make it face south. And then it would be the output of the AND gate, right? Coming from somewhere, right? And then also with the read line, so we would take the read line in. And then if the two were true, then we have a valid read signal. And then the same exact thing, sort of thing, going to happen if we go ahead and face it this way, which I learned is actually a key combo, which is pretty nice. And then we're going to take our right and take it over here and plug it in here. Then we're going to have to take the decoder and the two together with narrow gate, right? And then face it downwards. And then now that we know this, we would be able to go ahead and determine which is enabled. So I think the way we should go about this is move this unit over, take each decoder and bring it out somewhere towards the middle, right? Then we're going to go ahead and make sure that it's trimmed down to size for each line. And then we're going to go ahead and pass down the lines down through this little channel, essentially. Connect it here, and also connect it like here. Then we could go ahead and replicate sort of this logic for the next person over here. So let's go ahead and take this logic. We're going to need to space it just a little bit more. If I can, there we go. And of course we can always re-space it, right? Whenever we want, so we'll take it over here. And I want it to be like in line, right? I want it to be in line with it. So it actually needs to be over by at least one more. So I can do that. It's fine because it's not really hard to redo that. And then we would go ahead and attach it down to the rest of the line here. And then we would go ahead and take the other input here from the read line over here. Take this one and we'll pass it through the outside, I think. That might work better. The right line. And then we'll pass it through this decoder line, right? And we'd have to be guaranteeing that the line that we take from over here right would be taking the last line here. And then we would have to pretty much AND them together. So it would be an AND gate, narrow AND gate between the It would output to this line, that is correct, but let's go ahead and take away the wires here. Take an AND gate, drop it on the line here. We would also need to take this line down and across into the AND gate, then output it in such a way that it was easily connected to both. And I'm going to do this for every single one, and I'll go ahead and reorganize it for each one. And then we're going to take the outputs, right? And then pretty much we would tie every single output would be tied into one big line that goes across the bottom to the output pin. And that's the way that we would go ahead and do it. And I'll go and reformat this to look a lot nicer. And I'll see you guys in the beginning of the next video with the full version of this completed. Essentially, your rule is that you're going to take the output from the decoder, and it together into one signal line, throw it into the SRAM, and then we're going to have it hooked up to the write, read, and data lines, and pretty much use it that way. So thank you guys for watching. Please like, comment, subscribe, and I'll see you guys in another video with this entire thing fleshed out. It's not too hard to do. It's just going to be very time consuming, especially if I do it on camera. So yeah,